Okay, good morning, good afternoon, and good evening, everyone on the line. My name is Star Gao. I'm the GOBii application specialist, also your host for the GOBii web seminar. So GOBii seminar take place the second Monday of each month, 10 to 11 a.m. US Eastern Time. So for 2019 GOBii monthly seminar, we are completely open. We welcome all the experts. Volunteer yourself by contacting GOBii website or directly replying to the invite. We welcome people to host a webinar or recommend and nominate speakers. So for GOBii web seminar, we like to cover the molecular and genomic application use cases, also the data management and data ontology, curation, standardization, also different decision supporting tools. So for all these will be completely relevant topics. Feel free to nominate yourself or someone else. Also, GOBii seminar will be shared on public YouTube for the community to access to. So please just be aware during the seminar, mute yourself unless you have questions or comments. Also, we encourage everyone directly share your comments or questions on the chat button directly in the Zoom function. All right. So today, the seminar will be given by Dr. Umesh ROSYARA, and then his supervisor, Suzanne, will introduce the speaker. With that, Suzanne, please go ahead.
Yes, good morning or afternoon, everybody. In Mexico, we have 9 o'clock in the morning, so good morning. It's my pleasure to introduce our today's speaker in this web seminar with the title Genomic Data and Quality and Sample Quality Control, Workflow Development and Implementation in Wheat. So the speaker is Umesh ROSYARA, and he has been at CIMMYT and in my group since I think it's his third year, and he's the GOBii mid-breeder. So he's basically responsible for developing and designing strategies and tools within GOBii for the wheat program. And he, besides, does several research activities in the global wheat program itself. With that, I ask Umesh to start.
Okay, thank you, Susan, for the introduction, and Star for inviting me for this seminar. Good morning and good afternoon or good night, depending upon where you are. Whether you are listening us live or it will be recorded and in YouTube. We have similar seminar before about genomic selections. If you like, go back and see in YouTube probably. So today's topic is kind of broad topic. I'll be talking about quality control aspect of both genotypic data and sample quality, and how we are working on workflow development and the different aspect of implementation in wheat. I would have wheat examples, but it's more broader topic which may be applicable to other crops as well. Okay, let's get started. Today's topic, I would start with relevance of quality control, then I will talk about workflow development and the components like marker QC, sample QC, and different aspects of it, and finally how we are implementing. We are developing wheat QC panel and some collaborative tool under GOBii in development of QC tools to help performing QC and maintaining quality control in the database itself as well. So this is one of the story caught my attention. A farmer was cheated on seeds and he took his life away. So sad, right? That's a bad story to listen because he didn't get true to type seed. Another story caught my attention was a while ago, longevity genetic study did some GOS, and due to without proper control of the QC, the paper was retracted from Nature. This happens frequently. So with this, it looks like to us two sad stories, but this signifies relevance of the quality control, both genotypic data and seed itself. So these are few use cases that we people are thinking on. Is one of the paternity confirmation and hybridity, degree of hybridity, particularly if the male ster line is not, has some cells or not effective, like chemical control of that type of thing. And then another aspect is purity assessment, how much pure seed we have. So there are mixer, CIMMYT usually has this seed multiplication before yield trials, and then that goes to the international nurseries, direct release. So we want to make sure that the quality of our seed has maintained the required purity. And that's also important because although another aspect is how much is the material is still segregating. Another is genetic identity. We release the cultivars and then the farmer get it and they plant it. So how much we need to confirm that the farmer has the same cultivar as the breeders in the on station trials. So one important aspect is like impact assessment. We said that 50% of all wheat has CIMMYT lineages. So how can we scientifically prove it? Maybe marker-based data will help us to very precisely, although we can, so far mostly pedigree are looked at, but they may not be correctly recorded. And another aspect is the markers. So when I'm doing gene discovery, what's good marker and what's bad marker, what we want to use or what we don't want to use. And the result is that QTL may be false if we don't have proper quality control of the marker data. The similar implication is marker assisted or genomic selection. If you have too much error rate, then we need to work on bigger populations, and we may have to grow bigger populations so that we retain, and then there may be something false or true. So it's another aspect, and this may also impact somewhere on genomic selection if you have a higher error rate or you don't have good quality control. So these are the use cases that we think of. There's several ways. So it can be divided in two aspects. So first, we need a good genotypic data. So we need to have a genotypic QC. Once we filter it, then that data can be used for sample or variety QC, which is mostly sometime a quality assurance, QA. So QA and QC are two things we similar in nature, but when they are implemented, it's kind of difference, makes a difference in the just a philosophical difference. So we have as a breeding program, we have two products. Not breeding program mostly is seed, but within the research program we have genotypic data, which we want to quality control and use that data to quality control of the seed. Second aspect of quality control is the initial state, which we control the error. Not having, we control the error in different ways. And the quality assurance is we certify that we have this level of quality maintained. and marker data can be useful in both ways. So this is regular data use workflow, which start with sample collection to user, and we have database, and then different step has different QC measures taken. I'll go a little bit details in genotypic data QC now, so which includes both sample, batch effects, and the marker quality. Sample quality, sample call rate, and other type of identity type of analysis, and then batch effects is also important, and marker quality has different aspects, including reproducibility, genotyping error rate, minor allele frequency, segregation, distortion, etc. But they are not linear, so they are more interrelated. So what we want to see is what good samples depend upon the batch too. If a batch is bad, so we want to use only the good batches to judge the sample quality, and so marker quality too. So it's kind of a cyclic process. Use good markers to characterize samples, and good samples to characterize markers. And when we came to a satisfactory process, then we can we exit out of this, and post QC data can be used for several purposes. So use of control is very important, and different controls are used, like technical reps, universal checks, parent blanks. The objective is to avoid mix-up, reproducibility, error estimation, and pattern Mendelian error rate estimation, so on. So it depends upon the objectives, and they are being used. When it comes to genotyping error rate, it's always a trade off between, right? So one of why next-gen sequencing type of marker like GBS were popular initially versus the SNP arrays, because it's cheaper, right? And we can control NGS genotyping error rate by changing the coverage and depth, and also the error depends upon the calling algorithms, pipelines, and the sequencing technology themselves. In contrast, the SNP arrays, each array has some associated error rate, and the clustering algorithm that makes some error rate. So in wheat, we have additional thing to consider when we, in contrast to other regular diploids, where yellow hexaplot with homologous chromosomes and duplications and paralogs, homologs, homologs. That makes usually they retain is to filter out diploid type of segregations versus like hexaploid segregations, like making this 7 clusters, for example. So, but still it's not perfect. So this can create some type of genotyping error rate. Always null alleles, and then will aid another layer of complexity if we have 6 genomes and some of marker are null in one homolog. So genotyping error rate estimation, usually we need 2 genotypes at least to see the discount, how much match are there between them. And we can have essentially, we don't know which one is the reference, so there is like, we don't know the real truth. So there can be 6 potential error rates, and we can estimate genotyping error rate. So when you come down to true, if you know the true genotypes and the difference something, then it's just 2 error rates between 2 samples, and it's like a double, usually in the lower range of the value of alpha or beta, the error rate is double of the estimated error discordant rate. So one of the important thing to note is that not all the processes, all the methods we use are not equally sensitive to error rate. So for example, if you are doing GWAS for rare variant, you would like to have very high quality genotyping because your allele may be rare in this population, and we have to find it. So, but if you are doing some type of biparental QTL mapping, you can essentially identify the errors because there is so less recombinations going on. So it depends upon the method we're using. That's one of the key point thing. So another aspect is batch quality, which is usually provider thing to do first. We hope they do it, but even if they don't do it, we can quickly check if we know the batch. This is array, so they usually have two chips per batch. So you can see the problem with this batch. Next aspect in the marker quality depends upon call rate, the reproducibility, which is you need to have duplicated samples, and the Mendelian error rate. So call rate is one of the most important for characterizing failed or good markers. So one of important aspect is to set a threshold. What's acceptable or what's not. Usually the outliers are discarded, but each platform has different type of distribution. For example, if you have a GBS data, naturally it has more missing rate. If you apply to same filter as a SNP array, then you will discard a lot of your markers. Similar thing is for sample quality. Call rate is very important. It's mostly related with the DNA quality, then comes to reproducibility and the inheritance error rate, which is maybe associated with bad. If we have the parents, it may be related to the identity of the sample itself, or even its sample quality, or even DNA quality may be in problem. So call rate for each sample has some similar problem, and then what's failed and good sample depend upon your platform. Some platform inheritance has more missing data over others. So one of most important thing is sample identity, which may be basically correctness when you do any type of marker assay. You want to make sure that your sample is correct, means that intend to be, but it has more also to do with the patternity or purity or identity. It's a second layer, which we'll talk later. So identity, even if you have, like if you sample anything from our population, there is chance that at random these will have same alleles. So they may have same genotypic profile at random, so which is important to consider, right? So we should not consider this match just using one marker. That's so. So another aspect in quality control is relatedness, which is measure of inbreeding, and there are several measures, like I provided the example here. They can be helpful to find some problem samples, like you can see in yellow, they may be mixed, because we have like F1s from two parents, and then you get some very unrelated samples. And if samples comes with parent one, then it may be self of parent one. If it's coming with the parent two, it may be self of parent two. But it's often ambiguous to establish relationship, but it can raise question on the relationship. For example, sibling and parent offspring have same kinship coefficient. So it may not tell you the direction, but it raises the question of the identity of the samples. So the paternity tests are often done to test whether X is the parent offspring. So let's, with this backgrounds and workflow development, let me talk about the QC. We are developing QC panel, which has the objective of sample or cultivar QC, genetic, that will be used for genetic identification and purity testing. So major objective is not marker QC, but it's for the sample or genotyping, variety QC. So the guide that we select marker is that if you select closely related markers, you can, so distance between markers, then you'll not be able to separate between samples that are distantly related. So if you select, distantly related markers, then it will clearly distinguish between distantly related samples as well as the closely related samples. So one of the important aspect is the probability identity. So in this, if you have a low number of markers in random, you have higher probability of getting a genotyping profile same at random. So we need to see how many markers we need to get the power to discriminate. So that's power of discrimination. So you can see with different minor allele frequency, if you have a higher minor allele frequency, it will go up, and with a small. But the more difference is based on the number of markers we put on the area. Obviously, that's related with the cost too. So that's another part we are thinking on, how to optimize the power as well as the cost of the array itself. And it's mostly evolving thing. Yeah, another thing we need to always think about variation within Purelines. So we think like which cultivar is like uniform genetically, not really, because there should be always some segregation. Like if you even self 12 generation and then let it do whatever it do by itself, then still you can find some segregation after a while, for a while. But what breeders do is at up to some point, or seed growers will do some sort of rogging to pull out some phenotypically distinct, like early maturing or late maturing tall plant, usually tall or dwarf or maintain height or something. But still there is some hidden, so that may affect the identity type of analysis. That's we should consider that what's the tolerable difference within a pure line we want to have. So for doing QC, we have two data sets. One is 46K line, 46,000 lines with GPS markers. And then another is 1,100 lines with SNP array, quite a lot of markers. So you can see some population structure here. This is our workflow to develop QC panel. Basically, we filter marker for missing, and then minor allele frequency, population structure doing, and we cluster the markers. And then in addition to the chromosome is too big in wheat. Usually you can find, if it's opposite end of the chromosome, they are segregating independent. It's not perfect. Like for GBS tags, it may not be perfect physical position of the marker may not be perfect indicator of the linkages. So as a double protections, we do marker clustering and maintain within chromosome and the marker cluster in 2 ways. So then very high polymorphic markers used and then evaluated for the discrimination power that I'm talking about. And the same for 2 arrays, 2 data sets, and then we are already developing CASP assay, and then it will be used for identity, purity, and so on. So sample QC and the final panel will be released and used for different purposes. That's our essentially workflow. You can see how the power looks like. So this is just opposite of power, like the curve means that chances of having no non-discriminated pairs. So we have quite number of pairs compared and see how many times they have markers which are not different than 3. 3 is like to buffer. We need at least one difference to say it's different, but still we need a buffer because we assume that there is a genotyping rate which is different for different areas. So I think 2 marker difference is good enough, but at least we should keep 3 to be conservative enough. So we can see in breeding population, it's a very slow decline. So, and to get to 1%, you have to go to like 35 markers. But in diversity population, as expected, it's a very fast decline. But at the end, it's almost a similar trend if you go more than 30 markers. So that gives us an idea how many markers we need to really distinguish and what level of like discrimination power the array will have. So in next phase, we are putting this to use for the thing I talked earlier, like purity assessment, hybridity for identifications, which include like seed purity is one. We're testing this for like, we have the breeder seed goes to yield trials and then go to seed multiplications, and that was used to, we'll be using this to check the seed, how much seed mixture we have, and if we can catch some segregation distribution. Too much, it may not be like fine scale. And another aspect is F1 verifications and hybridity testing. So if a chemical hybridization agent may have some degree of selves, that's what our hybrid breeder thinks. And we want to see if they reach like some selfing, what degree is it? And then another is like mixture. Obviously, seed lots may have mixture, so we'll try to test to separate these 3 components. And another aspect is like identity confirmation. We are sampling some seeds from breeders, and we have gene bank. and to match the profile of gene bank using the array, and then see what level of match we have. So another aspect be background similarity is about QA, quality assurance. For example, if you have male sterline and a maintainer, then you have only one gene difference maybe. So there may be some more. So we want to make sure that this A is B is the maintainer for A and has more or less the same background. Same for near isogenic lines, right? So that type of confirmation may be helpful. So with this, like with the QC panel, and we always do gene QTL analysis always, and then the morphological data is always collected, like plant height or maturity or something like that. So if you can combine all this, we'll create a Germplasm profile, which is very strong, which may be very strong to say for cultivar identification and intellectual property management, including the thing we talked about, adoption, like how much variety adopted in very scientifically we can survey the old seed, even if we don't have a clue of any part. If you find a variety in farmer field and we don't have a clue where that is coming from, then with this type of profile we'll be able to find what's most likely. And we have stories like we find resistance of like a weed in a wheat, like a mixture or of type, and then we try to find what it is. It's resistant, so we need to give a identity to it. So next part, I've been involved in the QC GOBii QC tools. So maybe it's good to highlight some of things going on. Some of you may be interested on these tools. So quickly I'll go through this. I'm not going into details. And these tools will be used and being used in wheat as well. So PlaqueTech with JHI have some tools, pedigree verification, and similarity metric computation, graphical genotypings, and so on. So these are helpful for some QC. And the KD compute, with KD compute from that, a QC tool is being developed and will be integrated with GOBii GDM. So database, when the genotypic data goes into database, it does some basic QC and gets a QC report. So which has similar features. Do marker QC, reproducibility, F1 verification, graphical genotyping, and some desktop tools to do visualization and dynamic filtering. So let's talk about the second QD compute component, which is being developed with that, and it will be integrated in GOBii Genomic Data Manager. So it has features for marker QC, and most of them I already discussed in this presentation. Sample and batch QC, although it's very on active development, we are seeking input from users still. If you have a good idea, I would like to hear from you. Just email me. we are not public yet, so you might not have idea of what, but mostly this is under development. Some of you are already involved in this process. And genetic identity and graphical dynamic filtering is a very convenient way to filter out data and reload to the database or use for own purposes. So it has a very nice appealing graphical genotyping thing going on, which may be useful for looking at the pattern. So this is just an example. It's under development, so may have much improved version in future. We can compare marker QC parameter with the sample QC parameter and the graphical genotype together in one window. Yeah, this may be very good if you have very big data, like, and we have very many QC statistics. We can apply different filters, and you can see the trend. Like there are some white places, right? This marker may be like missing and so on. So it's even being improved, and we may spot some like recombinations if back like a biparental chromosome. So it's under development. So before concluding, two important points. QC is subjective, and it depends upon study, quality requirement, and platform, so on. But QC is important because it's related to the false discovery rate, error in pedigree, establishing genetic identity, a level of genetic purity, etc. So these 2 points are very important. So that concludes my discussion. Finally, I would like to acknowledge people who are involved in development of QC panel, and I thank you, Star, for inviting me to this presentation, and GOBii people are involved in all this QC tool development. It's nice to be part of that. And members of Global WHIT programs, and all of you who came today and listened to the talk. Thank you for your interest. I think we have about 15 minutes left. And I think we have some time for questions. Thank you.
Thank you very much. Here's Suzanne again. Any questions?
Hi, this is Kevin, Kevin Silverstein at the University of Minnesota. Thank you, Umesh, for a very nice talk. You discussed a lot about the QC after the fact, when you're basically looking at genetic factors and actually doing the genotypes and that. And you touched briefly upon the potential for sample mix-up and things of that sort, which in breeding is a small issue, but real. But more when you're doing impact assessment from the farmers can be a huge issue because of the number of times that samples change hands of people gathering stuff in the fields, often having to send their samples remotely to either within the country, depending on the country's requirements, or out of the country. And each time changing hands multiple times. You want to discuss a little bit about maybe best practices protocols of, again, you briefly mentioned maybe duplicate samples in each 96 well tray or things of that sort. Maybe want to discuss a little bit more?
Okay, yeah, that's an important point. Even if with the breeding program, it's about economy cost as well. If you if you want to relax your, like, if you hire cheap laborers, for example, to do rogging, then level of like quality mix up, even if experimental conditions is different in different situations. But as you said, when you go to the international, like we have a lot of partners all around, and they will release something, or then it goes in farmer hand, within farmer, then farmer to farmer, and which is not like so much commercially working there, so nobody controls the quality, flow of quality anywhere in the middle. So a variety called A may be not the same when it comes down to the farmer field. They may be calling it same, but it's like mixed up somewhere. So that can happen easy, but that's one of our now. So far, we're not depending a lot on markers on this aspect. So with development of QC panel, and as I talked about the profile, if we remember the profile, if we can create a QC panel, should be very powerful to find close to what it may be, right? So with if you combine with the other information we have, like we'll do like whether this LR gene, this gene, or persistent gene, or that gene, with the morphology, like it's tall plant or dwarf plant or something like that, that type of record will be very powerful in finding what reality is. But as you said, this can be a good project to do at the old stage, and but we don't have data on that aspect using markers. But yeah. That your question?
Yeah. Okay. Yeah. No, that's good. Thanks.
Yeah. Any more questions? We have time.
Hi, Umesh. This is Liz. Thanks for a really nice talk.
Hey, Liz.
Hey, I wondered in the development of your QC panel, whether you've buffered it in any way for changes in future market technology developments. I'm just thinking about whether you've selected markers that are going to be easily adaptable to future changes in how we run markers in different chemistries.
Yeah. So it's about so we have GBS technology. We tested GBS in one data set and SNP another, and combine them to make it a CASP assay. Then it will be Intertech probably panel. But when we have the sequence information and their location information, maybe we can package it in any technology we want.
Yeah, I'm just thinking about maybe selecting some loci that have very conserved flanking regions so that you can switch it to an amplicon-based technology in the future or whatever might be coming.
Yeah, that's a good suggestion.
Okay.
Yeah, even I think we can, if we know the location of these markers and the sequences, maybe we can redo that process to find, because we have plenty of markers to discard too.
Right, and CASP are very short primers, so it'd be nice to be able to reuse those same loci for future technologies by getting a good chunk of flanking region with without any indels or polymorphisms in them.
Yeah, that's a good point. Thank you, Liz.
Hi, Umesh. This is Star.
Hi, Star.
Thank you for the wonderful overview. And my question here is, I really like your summary on the 1% discrimination rate and corresponding to the 35 markers you compared generated. So my question for you is that this can be routinely implemented across very diverse breeding programs in all the weed breeding programs at CIMMYT?
Yes, that's the idea. So we put it. That's the idea. Because we have two panels, right? Breeding panel, which is more inbred, and then a lot of low polymorphism, more like sister lines, and so on. But diversity panel is really diverse, maybe catching some gene bank type of diversity. And then combine them together. Now we are evaluating in one panel with two type of situations, so that the array will be robust to differentiate both breeding type of situation and diversity type of situation.
So my next question is, what kind of strategies in implementing this on routine basis? For example, the vendors, platforms, and also the breeding field adoption, in which stages of their breeding program they will start doing this QC panel screening?
Yeah, we are open to discussion. Probably these are like seed purity. When seed multiplication is done to distribute to, we want to make sure that we have a good pure seed to be distributed, like 400 our partners around the world, or whoever requests the seed, we are sending the seed to them, the international nurseries. So that's one use case, routine basis, right? And if we want to like confirm identity, like we are setting up new research and you want to some identity test whether the seed I'm using is correct, right? That will affect your result very much after 5 years of crossing and selfing. You discovered, oh, the parent were not right. That type of situation, that's maybe one of the routines. And then the hybridity is another maybe routine to, like, we want to have a quality control upon true hybrid seed, right? We can work on, this can improve the efficiency of the hybrids. So better hybrids, in a more real hybrid versus the selves. Yeah, same as male line. So this can be a routine in several stages. But we should start with the purity, I think. We'll see how good our assay is. We're waiting for the results.
So you're going to assemble these QC panel markers, work with some vendors in the validation?
The validation, you mean?
Yeah, you're still in the establishing the protocol or validation stages?
No, we have been working with Intertech to develop Intertech, which we want to reduce the cost, like it may be like $4 at the end per array. But we're working with them to have some seed purity samples type of study, and then hybridity testing, then identity confirmation, and then the background similarity confirmation type of use cases. So we are testing our marker set for these purposes in smaller scale, and then we'll filter out the marker, minimum number of markers required. If like it's cheap, then we may use all of our markers. It's even powerful. So the economic type of analysis will be still have to figure out, but we're thinking with the Intertech, but it still will be open to anything that gets cheap and faster.
Sure, it's very nice. Yeah, thank you very much.
Yeah. Hello.
Hey.
Yeah. Good afternoon.
Good afternoon.
So I'm Simon Peter from Nigeria. Okay. I'm actually a PhD student under working. I'm also working on cassava regards error rate, development of tool for error rate. So I actually want to make a request. It's a nice presentation, but I want to is it possible to work under your lab for this so that we can implement it in cassava also?
Yeah, if you want to talk, we will discuss with Susan, and I think we are welcome if you want to talk with us. And
so I can talk to you later, and then we talk probably through the name and then discuss.
Yeah, we can discuss on how we developed. We are open to share our stories and things.
Okay. Yeah, thank you. So when you say call rate,
yes.
So what does it mean in a layman language?
Oh, sorry, I skipped it. I was a little fast on explaining things.
Yeah.
Call rate is like how much data you get over the total number of. So it's how much missing. For example, if you have for markers, if you have 100 samples,
okay,
one marker, then if you got 99 of data and one is missing data, then it's 99% call rate.
Oh.
Similarly, for the same for the sample. If you have 100 markers and one sample got one missing data in somewhere, then it's 99% call rate. So it can be marker call rate and sample call rate.
Oh, all right.
Yeah.
Thank you.
Good.
Thank you, sir.
Okay, thank you. So Umesh, just want to confirm, is that a missing rate and a call rate together sum up will be 100%?
Yeah, usually people like to talk about call rate. Some people like missing rate, but call rate is more optimistic.
Yeah, just look at the things from two different angles. Percentage,
yeah,
percentage to how the data.
Yeah, it's like who is not coming today or who is coming today.
All right. So more questions for Umesh? Okay, if not, we will adjourn. Thank you for the 24 participants attended today's seminar. We'll share the YouTube link and also the presentation slides and also Umesh's contact information. You can directly reach out to continue the discussion. With that, thank you all. Have a good day now. Bye.
Bye, everybody.
Thanks.